So my internship project was over magnetic reconnection and plasma acceleration. So what is magnetic reconnection? It's a phenomenon that occurs within plasma in intense magnetic fields. So it is a sort of breaking and reconnection of magnetic field lines. And I put that in quotes because magnetic field lines aren't physical things. They're representations of how fields flow. But this is the best description we have of it, as you will see later. Reconnection, I will show you later on, it accelerates and heats plasma, and this is one of the reasons that the corona around the sun is actually hotter than the surface of the sun. And so where does it occur? As I said before, it occurs within the solar corona as well as in geomagnetic storms. It creates coronal loops around the sun, as you see in the bottom left picture here. This is a picture taken by NASA's TRACE satellite telescope. And it also creates the northern and southern lights on Earth. So magnetic reconnection on the sun, by accelerating the plasma away from the sun, it creates jets of plasma that go in all directions. But when they eventually line up to hit Earth, they hit a shock into Earth's magnetosphere, and it wraps around Earth. And on the tail end of Earth, there's also magnetic reconnection there. And so the plasma jets that hit Earth, the energetic particles will then follow the field lines of Earth's magnetic field back to the northern and southern poles. This causes the plasma and energetic particles to ionize with atoms in the atmosphere. And that's how we see the auroras, is by basically the atoms in the atmosphere are being ionized, turned into plasma, therefore they're glowing. Like in bottom right picture here, this is taken by Zachary at NASA. And so how do we simulate reconnection? We use the reconnection, or the particle in cell method, to simulate reconnection. So this is treating it as a finite number of particles to be simulated, and it also separates the entire simulation into subgrids that can be calculated in parallel. So the resolution we had was 4096 by 2048 pixels. It was made up of 64 by 32 grids. And then each grid was 64 by 64. So that's how we get that resolution. And we used a supercomputer to actually get the resources to simulate this, as each grid was assigned at least one of its own CPUs so that we could run it in parallel. Plasma consists of ions and electrons. And so because of this and the size difference between ions and electrons, we can make a two-scale structure where in each scale, one of the particles is considered frozen in. So the larger structure would have ions dynamic and then the electrons frozen in, whereas a smaller structure would be flipped. And frozen in means it will be considered a sort of charge neutralizing background, or so one of the particles that is frozen in, they will move strictly, their gyro radius will move strictly along the magnetic field lines, whereas the other non-frozen in variable will be allowed to move completely dynamically in the simulation. And by having this two-layered structure, we're able to get all of the information that we need without having a overly complex simulation. And so analyzing the results, we simulated reconnection from the time of 0 to time 41. And in all of the figures, I overlaid the magnetic field lines, which you can get by getting the contour of the magnetic potential. But first, I will show the components of the magnetic field, and then the velocity and temperature of ions and electrons. And in all the figures, the saddle point or the center of the reconnection site is always marked by an X. And then in the temperature figures, as I'll explain more later, we see the whole picture rather than just one reconnection site like in all of the others. So this is the X component of the magnetic field. So this is simply the magnetic field running left and right. And as you can see, the top half and bottom half are moving in opposite directions. And these are pretty strong magnetic fields since the magnetic field lines are fairly close together here, at least in the beginning. So this is kind of, you can imagine along the center where that white line is, there's quite a lot of almost tension in the fields. And then as time progresses, they kind of warp. And so you can see that the parallel lines kind of disconnect from themselves and attach to each other. And they start to loop like this on the sides of the saddle point. And then as time goes on, the magnetic field lines begin to disperse, get kind of further apart, and the loops on the outside also tend to push out toward the sides of the plot. We can see this here again with the Y component of the magnetic field, but we're less interested with that than we are with the Z component of the magnetic field. So in all of these figures, we can see that there is the white space in the center that runs horizontal. That is evidence for what is called a current sheet. And a current sheet is it's a plane that of current that is created by the moving charges of the ions and electrons. Also, we can see in this figure, which is the third figure from the previous slide, that there's a formation of a quadrupole. So since this is the BZ, um, or the magnetic component in the Z direction, this is actually coming in and out of the page. So we see in the top left and the bottom right, it's actually coming out of the page at us. And then in the bottom left and top right, it's going into the page. And so this kind of, you can imagine it creating a loop here of magnetic field. Both of these are defining characteristics of magnetic reconnection. You will see both current sheet and quadrupoles in every form of, or in every reconnection site. And we also plotted the velocities of the ions and electrons. So you can see in the top, this is the velocity of electrons in the x direction. And on the bottom, this is the velocity of ions in the x direction. And you can see that the electrons tend to stay in this kind of flatter shape, and that's because of the current sheet, as previously mentioned. And also, the electrons and ions are moving in different directions, and that's because their movement is caused by the magnetic field, and therefore the opposite charges of ions and electrons will cause them to move in different directions. Also, the ions are much more massive than electrons. In real life, they are ion to electron ratio of about 2000 to 1. But in our simulation, we only had about 25 to 1 to make the electron gyro motion effects appear faster. And then here's also the temperatures. So at the top, we have the temperatures, initial and final temperatures of electrons. And on the bottom, we have the initial and final temperatures of ions. And in both cases, they heat up to multiple times their initial temperature. So in the first one, they heat from about 0.1, 0.2 up to 0.6. And then in the bottom, they go from about 0.5 to about 2. So this shows, along with the previous velocity plots, that magnetic energy is being converted into kinetic energy in form of both accelerating the particles and heating them as well. And we can see that further with these plots here. On the top plot, it is the reconnection rate of the simulation, so the rate at which reconnection is happening. And then the bottom plot is both the total magnetic and kinetic energies plotted over the time of the simulation. So the time plot, we see it's rising almost exponentially up until about 20 in the t equals 20 in the simulation. And then it starts decreasing down until about t equals 35, and then it plateaus and just kind of runs flat. For the energy plot, we see that total energy is constant the entire time, so we didn't violate conservation of energy. But we can also see the magnetic and kinetic energies kind of remain at the same values until t equals 20, and they swap values kind of. So the kinetic energy gains the same magnitude that the magnetic energy did. That finishes about t equals 35, which since both of these timestamps line up, we can illustrate using these that the magnetic potential energy is being converted into kinetic energy. And this process is both slowing down reconnection since the magnetic energy is not becoming as strong, and the kinetic energy is in fact accelerating and heating the plasma as its magnetic is being converted into kinetic energy. And that is the end of my presentation. I would like to thank the program for allowing me to be here, and if you have any questions, please ask.
Hi, my name is Flasmy, and thank you for watching this video. Make sure to follow us on our social media at CPH2AL on Facebook, LinkedIn, and Instagram. Bye!